Okay, good morning and welcome back. Please, I hope you can hear me. Cool. Okay, so as you all know, we have our exam coming up this Friday, right? Please, I will entreat you guys to either submit, either attend the recitation tomorrow. I was able to give the TAs a few pointers towards the exam, and also I think the Math Center also has a study a study guide review, right? So that would also be a good way to understand what's going on, right, on the review sheets. Well, you can also contact me if you still have any questions or you want to solve some of the questions together. Yeah, so that works. So on Friday, we have our third exam. Yeah. But before we start, please, do you have any questions for me? Any comments, any problems? Okay. So if there are no issues, then let's get to work. So today I'm going to continue from where we left off on Monday, right? On Monday, we're looking at optimization problems, right? And then I said that there were three approaches we are going to look at. So we were able to look at the case if the quantity we're optimizing is defined on a closed interval. For that one, we use the closed interval method, right? We did that. And then we also did the case for which we are using the first derivative test, right? So today I'm just going to talk about the second derivative test, which is the third one, right? So let me just quickly share my screen, right? And just quickly show you what we're doing. Right? So we're looking at this problem where a farmer is fencing a field, right? A rectangular field along a river. So for this one, we were able to get a constraint, right? Which is an equation which relates the variables from which you can solve for one of the variables in terms of the other. Now, this is in order to get the area in terms of a single variable. We got this, and then we got the interval to be a closed interval. So that meant we could use a closed interval method. We did that. We got the S to be 600, which was a critical point. And then solving it, we're able to see that, okay, the 600 is where the absolute maximum occurs, right? So that led to the dimensions of our 600 by the Y value, which we obtained by plugging the 600 into the constraint or the equation we got relating the variables, right? And then I also showed you the first derivative test. For that one, we do the usual first derivative test, like the ID test. But for this one, since you are searching for an absolute maximum, you have to be cautious, right? It should be such that that point that you are looking at, the function is increasing to the from the left, approaching that point, and then decreasing for the entire region as you move away from that point, so that you have something like so, right? If you're looking for a minimum, then it should be something like so, right? So that's the first derivative test, right? The last thing that we couldn't get time was the second derivative test. So that's what I'm going to talk about today, right? So let me move to the whiteboard. So I'm starting from here, right? So with this one, we have this function, right, that we are trying to optimize on this interval. Now, when you're trying to use a second derivative test, the first thing that you have to do is to find the critical points, right? So we do that by finding A prime, which will be equal to 2400 minus 4x, right? And then from here, we set this equal to 0, right? So that gives us 2400 minus 4x. No, let me not write the same thing here. I can write this as just add 4x to both sides. Then you divide by 4, you get x equal to 600. Right. So when you get x equal to 600, we have to make sure that we know that there is an absolute maximum occurring here. Please, not a local, right? Not a local maximum, right? In this case, we need an absolute maximum. So in using the second derivative test for absolute maximum or minimum, you just need to get the second derivative. Right. So as I was saying, this is one of the simplest approaches you can use. Right. So just get the second derivative. So the second derivative is a prime of x. And that's just going to be the 2400 go to 0 since it's a constant, and the negative 4x, so you have negative 4. Right. Now, when you get this result, you can see that the negative 4 is what? It's negative for the domain of a of x. Right? It's always negative, no matter what x value we plug in from that 0 to 1200, it's always going to be negative. Now, what this tells you is we know that the second derivative is used to check for concavity, right? So if the function is always negative, it has a second derivative always negative, then that means that from the interval 0 to 1200, the function is what? It's always going to be concave what? Concave downward, The function is like so, right? So because the function is concave downward along its entire domain, that means that at this critical point, which is a turning point, there has to be what? An absolute maximum. So this tells us that the function is concave downward. So at the turning point where we set it equal to 0, which is at the 600, there has to be what? An absolute maximum, right? So that's the second derivative test, absolute maximum. So get there. So let me say at 600, at that 600 at x equal to 600, right? So absolute maximum, right? So in summary, for the second derivative test, just get the second derivative of the function, check for the domain of the function, and see whether it maintains, right? Whether it's always concave upward or concave downward. Well, if it's always concave upward, then that means that if there is a turning point, a single turning point, then that has to be what? An absolute minimum. On the other hand, if it's concave downward, then if there is a turning point, then we are supposed to be getting what? An absolute maximum, right? So that is it for this one. So let me write a quick note here. So -4 for this, for the domain of this. Hence, an absolute maximum occurs at x equal to 600, right? So if you want to get the actual absolute maximum value of the area, you will just be finding, so the largest area will just plug the x value in the area. Right? So the largest area will be evaluated as what? A of 600, right? Which will be obtained by plugging it in this. And from the result we got last time, it's 720. Oh, the 7 is really bad. Yeah, so it's 720,000, right, square units. And then it also asks for the dimensions. And for that one, the dimensions are, we already have the x. The x is what? 600, right? So x is 600. And then from last time, you saw y to be what? 1200. So the dimensions are 600 by 1200, right? So that's the conclusion of the problem. So 3 options. Now you can use either one, depending on the question that you have, right? But for the closed interval, for example, you can't use the closed interval method if the domain is not closed interval. If the domain is not a closed interval, you can't use a closed interval method, right? But if you have a closed interval, you can use a closed interval method and all the other methods, right? For some of them, you have to restrict your methods to either second derivative test or first derivative test. I usually prefer second derivative test because it's easy, right? Immediately you get the critical point, just check the second derivative for the domain, right? And if everything works out, it will always check out that the domain will always either be negative if you're looking for an absolute maximum. So that means it's always concave downward, or it will be positive if you're looking for an absolute minimum. So it's always got concave upward, right? So yeah, so, but it's up to you, whichever option that you prefer. Please, any questions on optimization? Yeah, so for the exam, right, the optimization question that you'll be getting, optimization will be like a huge part of it, right? The optimization question that you'll be getting is going to be something similar to what you get on your homework. So make sure you look at the homework problems before you come, right, to take the exam. Yeah, because for optimization, I'm giving the hint because there are the range of questions you can bring is broad, right? It's very, very broad. So yeah, so that's a hint for that one. Please, any questions on 4.7? Anybody needs time here? Okay, so those are the 3 ways you can solve, you can optimize, right? Get the absolute mass of min. Okay, so then let's move on to, wait, that wasn't 4.5. 4.5 was sketch. I made a mistake here. This is 4.7. Yeah, then the next one is 4.9. Anti-derivatives. Okay, let me go to the so that's 4.7. Let me slide through so that you guys see that we are done with this one. Okay, so we wrap this up. Yeah, so on the slide, right, it's showing us the second derivative test. You see, let me try and show you this so that in case you're using the slides, you know what to look out for. Why is it not pulling? Yeah, so on the slides, it talks about the first derivative test for absolute extreme values here, right? And then the second derivative test, briefly in this like square brackets. Alternatively, you could observe that A prime prime is this, but I detailed everything on the notes. Yeah, so that's it for that one. Now let me go to 4.9 for antiderivatives. Okay. Please, I'm sharing the PowerPoint for 4.9. If you can't see, do let me know. Okay, so 4.9 is antiderivatives. Now, in chapter 3, we focused a lot more on getting the derivatives of functions, right? Let's say we have a function f of x, and then we get the derivative, which is the instantaneous rate of change, which was f prime, right? And then we got f prime. But it's not always the case that we are interested in the derivative. Sometimes we may have a function which is a derivative, and then we may be interested in the original function, which we took the derivative of to get that current function, right? So that is what we call antiderivative. So these are examples of such cases, right? A physicist who knows the velocity of a particle may wish to know its position at a given time. Remember that we learned that the velocity function is the derivative of the position function. So if you're given the velocity function and you want to get the position function, you are kind of like reversing the differentiation that you did, you see. Now the second case says an engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount of leakage over a certain time period. Now, this one is also looking at a derivative, the rate at which something is leaking, which in this case, which is decreasing, right? It's a rate of change. So that's a derivative. Now, if it wants to know, if the person wants to know the amount, then the person is trying to reverse this derivative. Well, how do you get the rate of change? Is it change in amount over change in time, the instantaneous change? You see, so if you want to reverse it, like it's the same, it's similar to the first case where we have the velocity and we want the position. So we are still reversing differentiation. Now, what about the third one? We have a biologist who knows the rate at which a bacterial population is increasing, might want to deduce what the size of the population will be at some future time. Right? So this is still the same thing. We have a rate of change. In other words, you have the derivative and we are trying to get the what? The function which we took the derivative of to get that derivative. You see, so kind of like reversing the differentiation. Right? So these are examples where this becomes practical. Right? But let's zoom in on this. Right? So this one says in each of the cases that we talked about, for antiderivatives, you're going to represent them by something like uppercase, right? But I'll use some other notation, which I'll talk about as we proceed. But it's usually uppercase, right? So if you're given a function f, then this uppercase is what we used to stand. It's not like something conventional, but you're going to use that for now, right? Something we used to stand for that. When you get to chapter 5, you have better ways of writing this. But for now, yeah, you just do the uppercase of it. So if you have a function f, which is the derivative, and you want to reverse that differentiation, then you get something we call an antiderivative, which we represent by the uppercase f. Right? So we define a function uppercase f as an antiderivative of a function f, lowercase, on an interval I, if the f was what we took the derivative of to get the lowercase f. You see, so the antiderivative is the function that you took the derivative of to get that f, the lowercase f. You see, so kind of like reversing differentiation. So whenever you do antiderivative, the question is, what function did I differentiate or will I differentiate to get this current function that I have? You see, that's the idea for antiderivatives. Please, any questions so far? I hope it makes sense. Okay, so now let's go. So we start with x squared, right? So suppose you're given a lowercase f, you have this function, s squared. And the question is, what function did you differentiate to get this s squared? In other words, what is the antiderivative of s squared? What do you do? Okay, well, for s squared, let's look at this function directly. Well, if you look at 1 over 3 s cubed, right, then the derivative of 1 over 3 s cubed, let's do that, right? So if f of s is equal to 1 over 3 s cubed, then the derivative, right, then f prime of x is equal to what? For this one, constant multiple rule, ignore the 1 over 3, and then differentiate this by the power rule. So that'll be your 3s squared, right? So that'll be equal to what? The 3 will cancel out. That'll be s squared. You see, that means that 1 over 3 s cubed is a function which we differentiate to get the s squared. So 1 over 3 s cubed is what? Is the antiderivative of s squared. Is the antiderivative of s squared. But the thing is, if I just write Suppose I write, I'm saying 1 over 3 s cubed, right, is the antiderivative of s squared, right? What if I have something like 1 over 3 s cubed plus 2? I could change it, right? What about 1 over 3 s cubed plus, say, 100? Now, for either of these cases, for either this case or that case or this case, all of them, their derivative is what? Is s squared, right? Their derivative is s squared. That means if I have the s squared and I want to think of a function whose derivative will give me that s squared, the constants will be missing, because see, if you differentiate the constant, you get 0. So if you are reversing the process, the x structure, you can get the antiderivative, but the constant, you can't know exactly what constant it was, because if I'm giving just s squared and I'm reversing the whole process, it could have been that it was this function or that function or this function. Although the x structure, what I mean by the structure with the x is 1 over 3 s cubed. Although the 1 over 3 s cubed repeats itself, right? So that one I know for sure what form it will take, but I don't know exactly what the constant will be. It could be 0, it could be 2, it could be 100, it could be anything, right? So to get a much more general antiderivative, we say, okay, now, instead of just saying the antiderivative for s squared is 1 over 3 s cubed, to account for maybe a constant which was there, which we differentiated and disappeared, we're going to add something we call an arbitrary constant, c, right? An arbitrary constant c. So the c will represent any constant which was part of the antiderivative, which has been lost, right, as we differentiated. So that means that the general antiderivative is not just going to be 1 over 3 s cubed, but it's rather going to be what? So for s squared, the antiderivative is what? The general antiderivative is going to be 1 over 3 s cubed, and then we add this uppercase c, an arbitrary constant, right? That's what it stands for. So that's the general solution, right? So these are like the building blocks. I'm going to show you how you get each of them, but most of the time you fall on the rules of differentiation, right? They'll be very important going into this. Now, please, any questions on this? Next, I'm going to show you how we get it for, you get the antiderivative, at least the structure for the x, and then always you add your arbitrary constant. Any questions so far? Okay. Anybody needs time on this slide? Okay. So the theorem says, so suppose here still, we are looking at uppercase f being the antiderivative of lowercase f on an interval. Then the most general antiderivative of the lowercase f on the interval is given by what? There's a structure which depends on x, and then a constant c, right? An arbitrary constant, right? Yeah, an arbitrary constant. Okay, please, any questions on this? So this is just giving us a conclusion. So if you have f of s equal to s squared, and then the antiderivative will be 1 over 3 s cubed, and then plus c. Any questions on this? Okay, now let me establish, this is a power function. So let me establish how we get the antiderivative for power functions. So let me go to the whiteboard and show you that. So you remember that for power functions, right? We said, recall that when we have d of dx of x to the power n, how did we get the derivative? Oh, it was just bring the power down, and then what? Subtract 1 from the power. So this is a derivative, you see. Now, for antiderivative, we are reversing this process. So the question is, how do we get from here to that x to the power n, which was the original expression that we took the derivative of to get this? So if you have this, how do we reverse to this? Right? In other words, how do we get an antiderivative involving a power function? Well, to get to s to the power n, all that I have to do is I have n x n minus 1. Well, I can just add 1 to the power, right? If I add 1 to the power and then divide by the result, right? So what I get is n plus 1, right? So 1 to the power here, and then divide by the same thing. Let's see what happens. Well, for that one, the exponent becomes n minus 1 plus 1. That's just n. and then the denominator also becomes n minus 1 plus 1, which is also n. The n's cancel out, and then I have s to the power n. Nice. You see, so what this says is, whenever you're going to get the antiderivative of a power function, right, ignore constants. Constants is just like how we did it for the derivative. Just ignore the constants. Is someone stuck? Okay, so ignore the constants and then focus on the power function, right? So the power function, the way you get the antiderivative is always add 1 to the power and then divide by the result that you get, right? So for example, for the f of x thing that we're looking at, right, f of x equal to s squared. If you want to get the general antiderivative for the s squared, since it's a power function, the power rule for the for antiderivatives, right, it's always what? Add 1 to the power, divide by the result you get. And please don't forget your arbitrary constant, right? So if you simplify this, you get s cubed over 3 plus c. So that's how come they are getting that result. They're able to decide that that is what the antiderivative of s squared. Now, whenever you want to check your antiderivative result, you can always differentiate the function that you have to see if you get the function you are given, right? So what I mean by that is, if you want to test that this is correct, let's differentiate this. If you want to be 100% sure, right? So you differentiate it, you get s squared, which is original, right? So please note that for power functions, that is how we do it. Just add 1 to the power, divide by the result. Okay. Please, any questions on this? I hope you understand it. This is going to be very key, right? Very important. Now, let me ask you this. What about something like, suppose we have small f equal to, say, s to the negative 1, or which is the same as 1 over x. Now, for this one, is the antiderivative also like a power function, add 1, divide by the result? Well, let's try it and see. Right, this is not the right thing, but let's try it. Okay, so antiderivative, okay, since it's related to power, okay, why don't I add 1, divide by the result? And let me bring my arbitrary constant. Now, the moment you do this, you notice that you have negative 1 plus 1, which is 0. So s to the power 0, well, no problem. But then the denominator will be negative 1 plus 1, which is 0. This is undefined. You see, it doesn't work. Maybe you have to think of other ways of doing this. Then the question will be, for 1 over x, the question is there a function whose derivative is 1 over x? Do you remember a function which we differentiate to get 1 over x? Anybody? What function do we differentiate to get 1 over x? Perfect. Thank you. That is true. So for this one, rather, we can use this power rule thing, right? So whenever the power of the x is negative 1, you can use the power rule approach for the antiderivatives. You have to know that, or remember that the antiderivative, or what we differentiate to get 1 over x, is what? Is ln of x, right? So ln of x. Okay, let me see. I want to do something else. Okay. Plus c. Well, perhaps this is important. Let me write it here again. ln of x. Okay, you wait. I'll do it on the next slide because I have to explain some other stuff too. But please, you need time on this. Any questions? I'll do it on the next slide. Okay, so now let me conclude here. So we are just formulating all these stuff. They will be very, very important moving forward. So if we have f of x equal to 1 over x, or x to the negative 1, the antiderivative we just saw is going to be what? ln of what? X plus c. But there is a big but here, right? The thing is, don't forget that you can't take the log of a negative number, right? And when you have the original 1 over x, the domain is what? All real numbers except 0. That means the x for the 1 over x can take on negative numbers. Do you see? So when you try and rewrite the antiderivative, you have to make sure that the function is not, the function is always defined. So since x can take on negative numbers, the way to make the function always defined for ln is that you can't just say it's ln of x, right? Because if the s can be negative. So you rather say ln of what? Absolute value of x. Very important. Right, so the antiderivative of 1 over x is what? Ln of absolute value of x. So that when the x, in case the s is negative, the ln of that will always be positive, right? But if the question already says that x is always positive, then you can just write ln of x plus c. Please, I hope you are okay on that point too. Right, so 2 things. We've learned how to get the antiderivative for power functions. And for the power function, you say when the power is -1 or the function is 1 over x, the antiderivative is what? Ln of not just x, because x could be negative. It's ln of absolute value of x. And then you add plus c. Let me see. We'll have, yeah, thank you for the question. Yeah, so it will always have plus c. And in your homework is what do you call it? It's capital C. So note that in your homework, if you use lowercase c, to say it's incorrect. It always says capital C or D. Sometimes if you're writing more than one, it will say you have to include D. Yeah, you're welcome there. Okay, please, any questions so far? So you've established 2 antiderivative for 2 of them. General power rule and then 1 over x. Any questions on them? Okay, so with those 2, let's go back to the PowerPoint. Okay, so for the PowerPoint, we are still explaining what the result of the antiderivative means, right? Because the antiderivative has, for example, when we had the f of x equal to s squared, we said that the antiderivative is what? Is f of x equal to 1 over 3 s cubed plus c, right? Because the c is an arbitrary constant, that means it can take on, it could be any constant at all, right? So because it can be any constant, the general solution, the general antiderivative is always going to be a family of functions. What we mean by a family of functions is the s structure is the same, but then the c is changing. So it's just like you are shifting the function vertically, right? So either you're pushing it up or down, right? So it's just a translation, a vertical translation, right? So this is going to be a solution. The black is going to be a solution. So that's the equation for the black curve you see here. And then we can change the c to 2. That's also going to be a solution. And change the c to 1. That's also a solution. Can change the c to 0. That's also a solution. So it's a family of solutions. So that solution you see here is a family of solutions. So that's your antiderivative, right? Okay, please, any questions on this idea? Anybody needs time on this slide? Okay, so now with this, let's do this example. Please, for this one, I will need your help to figure this out, right? So let's try this one. This one says, find the most general antiderivative of each of the following functions, right? So for the first one, you have f of x equal to sine of x. So we need a antiderivative. So my question is, what function do we differentiate to get sine of x? So A, what do you think? I need your input. Please help me out. There is a function, when you differentiate it, you get positive sine of x. What is that function? Thank you, thank you. I see some comments. Oh, perfect, perfect, thank you. That's negative cosine, right? Please note, the derivative of cosine is negative sine. So if you want to negate that result and get positive sine, you have to do what? The derivative of negative cosine. So that means the antiderivative for sine is negative cosine of x. But please, what are we missing? Perfect, plus c. Please don't forget that. Okay, awesome job. Now, what about b? What is the most general antiderivative? I'm just writing the results will be right here. Everything will be on the board. So what about b? What is the antiderivative for this one? Anybody? Okay, I have ln of x plus c. Close, very close. You're almost there. Don't forget, it didn't say x is positive. Perfect, perfect. So the general antiderivative is ln of what? Absolute value of x plus c. If they say s is positive for this, then you can just say ln of x. But if they don't say, then s can be negative. So you have to say ln of absolute value of x plus c. Very good job. Now for c, the n is not negative. It's not -1. So s could be to the power any number. right? Except -1. But if it's -1, then it becomes part B. So can anyone please help me with the general antiderivative for C? What is that one? What do you think? Anybody? Don't forget it's the power function. It's S to a constant. So what do we do? Anybody? Awesome. Okay. Thank you. Thank you. I was going to say, so what is left? Perfect. Plus C. Didn't forget plus C. Right. So by the power function, the rule that we learned was, as long as the power is not -1, all that you have to do is just add 1 to the power, divide by the result. And then don't forget your plus C. And that's it. Right. Yeah. And that's all on this. Now you see the solutions here. It's just going to explain, and yeah, just give you the result. Right. So for the 1/x thing to ln of absolute value of x. Right. So it's talking about the fact that x can be negative. So that's why we bring the absolute value. Right. Yeah. And then for the power rule, right, the reverse of that is just add 1, divide by the result. But please make sure that the power is not -1. On the other hand, even if the power is -1 and you do it, your mind will be brought to the fact that you made a mistake because the denominator will be 0. So it will make the whole thing undefined. So you always see that you made a mistake. Yeah. Okay, so that's it for this one. Please, any questions so far? It is just explaining what we did. Right, so you need the rules, right? The differentiation rules that you did, just a reverse of them, right? A reverse of them. So the differentiation rules are very important. Now let's walk briefly through this, right? So if you have a constant times some function, it's like the constant multiple rule still here. When you have a constant attached to some variable, just ignore the constant and focus on the antiderivative of the variable function, right? So that's what this is saying. Right. Now the antiderivative of the sum of functions is the sum of the antiderivatives. And whenever it's s to the power and where the n is not -1, it's just the power function, right? So n plus 1 over n plus 1. Now for each of these cases, we are always going to add plus c. So please don't forget. Right? So if it's 1/x, it's ln the absolute value of x. For e to the x, remember that the derivative of e to the x is e to the x. That one is easy, right? So the antiderivative is still the same thing, e to the x. Now for b to the x, the antiderivative is b to the x over ln of b, right? And then for cosine, remember that the derivative of sine is cosine. So if you want the antiderivative of cosine, it's just sine, right? And then for sine, it's negative cosine, secant squared. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent, right? Secant s tangent x. The derivative of secant s is that. So the antiderivative of this is this. So it's just a reverse of all the differentiation rules that we learned, right? So if you have 1/1 plus s squared, it's antiderivative is tan inverse of x, right? Now you're not responsible for these two. These are hyperbolic functions. They are hyperbolic functions. You don't need them. They are functions of exponentials, but you don't need them for these. Yeah. Okay. Any questions here? Anybody needs time here? Okay. Now this is just saying that this is just a reverse of the derivative. It's just talking about the table, right? Yeah, so it's not much on this slide. Yeah, so now let's work more examples. So I start with this, right? So find all functions G such that this. So this is like the most general antiderivative. So let's do this. So solution. So for this one, I have J prime of x equal to 4 sine of x. But then when I get here, looking at this expression, you can see that it doesn't look like something directly that I took the derivative to get this, but it involves power functions. So perhaps I can make my life easier by simplifying. If I simplify, then it becomes something like a power function. So this s to the power half x. You see, if I simplify, right? So sometimes it's not directly that you get the antiderivative straightforward. You may have to simplify. So this is a good example. So let's first simplify. I have J prime, so 4 sine of x. And then this one, the x's will cancel. So I have 2x to the power 4. And then for this one, the s down here has power 1. So by the law of exponents, this s to the power half minus 1. right? So that gives me G prime of X equal to 4 sine of X, and then plus 2 s to the power 4 minus s to the power negative half. Okay, now when I get here, now the G prime is simplified in a form that I can easily get the antiderivative for, right? So let me walk through and get the G of X. Now for the other notation that I was talking about for antiderivatives, for here, I'll be using uppercase, do you see? Because the function here is expressed as G prime. So I know that the antiderivative is just G of X. You see, if I were given G of X as like the derivative, then that one, the antiderivative, I could use an uppercase. But here, they have used G prime as the derivative. So if I want to reverse it, then I'm getting the original G that I took the derivative to get G prime, right? So for this case, I'll use just G of X. This is what I meant when I said I'll talk more about the notations later on, right? So this is it. So for here, I'll just say G of X. Now let's walk through this. Whenever a constant is attached to some function which depends on a variable, just ignore the constant. So 4 can wait. Now the question is, what do we differentiate to get sine of X? We just saw that that's what? It's negative cosine. So I have it for that. And then I go here, a constant attached to some variable, just ignore the constant, right? For the s to the power 4, how do I get the antiderivative? Oh, just add 1 to the power, divide by the result. Awesome. As long as the power is not negative 1, we can do that. Now, what about this one? Let me bring my minus here. For that s to the power half, perhaps I should write, okay, let me say, so we just add 1 and then divide by the result, same thing, right? So the power function at work, plus 1. Let me write it well here. So G of X equal to negative 4 cosine of X, and then plus 2x to the power 5 over 5. And then minus, you have x to the power negative half plus 1 over negative half plus 1. And then you are missing something, plus c, right? Please don't forget that. Let me try and squeeze this here, plus c, right? Now, one other thing, when you get antiderivatives on your exam, please don't focus on simplifying. The question will accept it here at this level, right? You can just plug this in and you are done, right? As I said, if you try to simplify too much, where you don't have to, you will be wasting a lot of the precious time, right? So note that. But for here, let me just simplify. So you have G of X equal to negative 4 cosine of X, and then plus 2 over 5 s to the power 5. And then negative half plus 1 is 2, right? So that'll give me minus 2 s to the half plus c. And that's my answer. That's my antiderivative. Is there any part or any step you don't understand? Any questions?
Where did the negative 2 come from?
The negative 2. Oh, okay.
Yeah,
so,
this one.
Oh, yeah. So I see this one, right?
Yeah.
Okay. So you see that, let me, here is not, I can't change colors. Let me get off here. Yeah. So let me use maybe black. Yeah. So you look at this, right? The negative half plus 1 here is half from here, the denominator here. You see this one? That one is half. So you are getting something like negative x to the half all over 1 over 2. So it's like 1 divided by 1 over 2.
I got it. I see.
And then that's, yeah, you're
Yeah.
welcome. Okay. There's always this trick that I use. I've been using it since I don't remember. I don't even remember. When you have A over B, I don't know if I've said this in this class, over C over D. You can make your life very easy. You don't have to write this out and do division, do times, and roll it back. No, you can just take the bottom here, multiply the top, and take the bottom here, multiply this bottom, this top here. So the quick thing that I did was for the one here, I just saw that as 1 over 1. So take the 2, multiply the 1 on top. So 2 over 1 times 1, 1. 2 over 1 is 2. You see, so that's the trick I used. Okay. Now, you saw that, so now let me get back to a bigger PowerPoint. Now you saw that I told you in 3.8 that an equation which involves the derivative and the function is called a differential equation. But for differential equation, you'll be focusing more when you get to like Calc. Okay, you start a bit in Calc 2 and then you do more in Calc 3, right? But Yeah, sometimes we are not interested in getting the general antiderivative, right? Sometimes we want the exact C, right? So we want a specific function. So to get a specific function, we may be given some extra conditions so that after we get the general antiderivative, we can solve for the what? The arbitrary constant so that we get the exact constants and then we have a specific function. So that's another twist to this. So let's look at some examples, right? So for example 3, we have f prime equal to this. And then we are given a condition. We are told that f of 0 is -2. Right? So because f of 0 is -2, we can find a specific solution. This won't be a family of solutions. We can get a specific solution, right? So let's try and get the antiderivative first. So solution. Okay, so I start with f prime. It's just e to the x plus 20 times what? This 1/1 plus s squared. So I go, okay. Now for the antiderivative, I can rewrite this as, oh, what's the antiderivative for e to the x? Oh, e to the x is simple, it's just e to the x. Now for this one, it's a constant, and then, so I can ignore a constant because it's attached to some variable function of x. Now what's the antiderivative for 1/1 plus s squared? Oh, that one I know is what? It's tan inverse of x. And then please don't forget your plus c, right? So I have the antiderivative, but this one is the general solution, right? The most general antiderivative. But then because I'm given an initial condition, I can solve for the C, right? What do? I just evaluate the initial condition on the solution that I got, and then I'll get my specific solution. So with that one, if I want f of 0 to be equal to -2, I can say, okay, so f of 0 is the same as what? F of 0 means e to the 0 plus what? 20 tan inverse of 0 plus c. That will be equal to what? -2. Now, what is e to the 0? E to the 0 is 1. And then plus tan inverse of 0. Tan inverse of 0 is 0. Right, so that will go to 0. So I have 1 plus c equal to -2. And then solving this, I'll get c equal to -2 minus 1, which is -3. Now, I've been able to solve for the what? The specific arbitrary constant. So I get a specific solution for f. So therefore, I can say f of x is e to the x plus what? 20 tan inverse of x, and then -3. So that is a case where you can get some conditions to get the exact solution. Please, are we clear on this? Okay. Now let me add some extra information. Now note that if you recall, right, the derivative of tan inverse is equal to what? 1/1 plus s squared. True? Now the derivative of cotangent inverse is equal to -1/1 plus s squared. So in this case, the antiderivative can have two forms. Someone could have also said, well, my antiderivative is f of x is equal to the e to the x will be maintained. But when they get here to the 20/1/1 plus s squared, well, you can see 20 times 1/1 plus s squared as -20 times what? -1/1 plus s squared. Right. So if you look at this, this is also the same as what? -20 times -1/1 plus s squared. Right. So if I'm able to see this as this, then I can also say, oh, it's fair to say that this is also -20 cotangent inverse of x plus c. And I'm not wrong. It's still going to give me the same result. Just went to the next slide. Yeah, it's still going to give me the same result. So just note that for inverse trig functions, sometimes you can have more than one solution. Right. So just note that. So this is going to be important in a multiple choice. Right. In a multiple choice, it's going to be crucial. So you'll be looking for tan inverse, but then there'll be negative cotangent inverse, and you say, oh, I can't see the answer. So probably none of the above, but then your answer will be there. Please, any questions here? Okay. Anybody needs time here? Okay. Now let's do more of these initial conditions once. So now for this, let's do it together. So I have f prime prime equal to 12s squared plus 6x minus 4, right? And I'm giving those two initial conditions. So let me try and get the antiderivative. So to get to f, right, the question says find f. Now, because I'm at level f prime prime, I need to do 2 steps before I can get to f, right? So let me first get f prime, which will be the first antiderivative. So constant power function. So add 1, 2 plus 1 divided by the result. And then 6x, that one is 6s power 1 plus 1 divided by the result. Now, whenever there's a constant, just multiply the variable by that. Because remember that when you differentiate, say, 2 times x, the derivative of 2x is what? Is 2. So if you just have 2 and you want to get the antiderivative, just, in my previous class, they used to say slap the variable on top, something like that. And it always works to remember that. I don't know why it just came to mind. Yeah, so if you see the constant there, just slap the variable on top. So you just have minus 4x. Then please don't forget your arbitrary constant. All right, so that's level f prime. We simplify it a bit. This is 3. 3 goes here 4. So you have 4s cubed. This is 2. 2 goes here 3. So you have 3s squared. Then minus 4s plus c. That's level f prime. But then the question is asking for f. So you also get, you have to get another antiderivative. So that means we go to f. So that one to ignore the constant, add 1 by the power function, like the antiderivative of power functions. And then this one's 3, add 1, divide by the result. And then this one is 1, add 1, divide by the result. And then for the c, it's a constant at this level. So you slap the variable on top. Now, because I don't want to repeat another c to create confusion, we use the letter d when there are more than 1 antiderivatives. Right, so this is my general function. But the question has given me some initial conditions. So I can use those initial conditions to solve for the specific c and d. So I try f of 0. F of 0 will be what? Well, let me simplify this before I let me simplify. Here I can erase. It's too bad. Yeah. So f of x, this 4 cancels, so s to the power 4. This 3 cancels, so that's s cubed. And this 2 cancels, that's 2s squared. And this plus cx plus d. Yeah, that's much better. So if I have f of 0 equal to 4, then what that means is 0 to the power 4 plus 0 to the power 3 minus 2 times 0 squared plus c times 0 plus d. Right, so all the zeros will go off. So I just have 4 equal to d. So my d is 4. Right. I'm also giving another condition. Perhaps this one will give me the value for c. Right. So f of 1 equal to 1 implies what? Plug in 1. So 1 to the power 4 plus 1 cubed, and then minus 2 times what? 1 squared. And then plus what? C times 1 plus d. But d is known to be 4. Please, I hope you're okay so far. Any questions? So we have 1 equal to this 1 plus 1, 2, and this is 2 times 1. That's so they will cancel out. Then you have c plus 4. So if you do the subtraction, you get you subtract 4 from both sides, I guess equal to -3. So that gives me my final answer of what? This s to the power 4 plus s to the third minus 2s squared minus 3x plus 4. And then I'm done. So there's the function. Please, are you okay with this? Any questions so far? Okay. And the exam covers up to this, right? So just know how to do this stuff. Anybody needs time here? Okay. Now let's go to another application. Remember that we said that when you have the position function, the derivative of the position function is the velocity, right? And the derivative of the velocity is the acceleration. So if you are given acceleration, we can go back to velocity by getting the antiderivative and then go back to the position function. So let's look at an example. And just as we had for the initial conditions in the previous examples, we can also be given initial conditions here and then to solve for the specific position function or velocity function. So let's look at this problem. This is the last problem for this section. So a particle moves in a straight line, right? And you're given the acceleration to be 6t plus 4. They're given the velocity as 0 to be -6 and the displacement to be 9. We have to find a position function. So for this one, let me do this on a whiteboard. This will be the last thing I do. Example 6. Is it example 6? So a of t, is 50. Okay, it's 50. Okay, it's 50, it's 50. Okay, let me not take too much time. Yeah. So yeah, let me end here. So on next time, I'll just do this example. It's not too bad, but yeah, I'll do it the next time. And then we continue from here. But then you'll be getting anti-derivatives. I've showed you the one where we have initial conditions, so you're getting them still. Okay, so on Friday, please make sure you come on time. As we have our tester. If you have any questions, feel free to reach out to me. So that's all for today. Please make sure to try and go to the recitation tomorrow, right? And then the Math Center review. Yeah, that's all for today. Thank you for your time. You are welcome, guys.